All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing? Good to hear. All right, so today's off. This is an off week, so we don't have any answers to do today. So we just have a lecture, but we're just kind of continuing right along. So on Tuesday we went over boundary conditions, and today is kind of part 3 of kind of the basics of FEA, or at least what I consider to be the basics, which are material properties. Okay. Now I will say material properties is I think probably the one thing in this class that I think is probably we're not paying enough attention to, just because we're doing a lot of other things with meshing and the boundary conditions. The field and the theory behind material properties goes very, very, very deep. So then, and honestly, there's a lot that even I don't really know too, because I mostly just I mostly use kind of the simple material properties, but there's definitely a lot more that there is to learn. So we'll cover the basics today. I mean, definitely everything that you're going to need for this class, but for a lot of the more interesting applications for FEA, and just kind of structural mechanics in general, material properties are kind of where it's at. So I wish we had more time to spend on this, but we only have just one day. So I'm going to try to cover as much as I can today. Linear elasticity, isotropic elasticity, orthotropic and isotropic plasticity, hyperelasticity. So it'll be kind of a very quick survey of everything material properties. Okay. Any questions I can answer before we get started? Okay. All right. So let's go ahead and get started with the lecture. Okay. So topic for today is material properties. Okay. So what are material properties? So material properties, they refer to the physical parameters of the material that affect how the material responds to physical forces. So every material on this earth is composed differently of different kind of molecules and atoms, how they're all bonded to each other, and that affects basically how they respond to physical force, right? So material properties, is not anything new. So you've definitely covered them before in previous classes. Okay. So some examples that you most definitely have heard of before will be things like density. Density is an expression of the mass of material, okay, or how much mass is packed into a fixed volume. Okay. More specifically for what we're doing, things like the Young's modulus. Poisson's ratio. And of course, there's many more properties as well, but those are kind of the basics to kind of get started. Okay. So every material has different different values for these properties. Okay. And in terms of FEA, it's important to get these properties right, because ultimately, like as we've been discussing for the last few weeks, ultimately our finite element simulations are going to aim to emulate or replicate a real life situation. And if you don't get the material properties correct, if you choose the wrong material, or you forget to change the material from the default, your results are going to be wrong. Okay. So mathematically, right? So remember, finite elements is nothing more than just a way to solve these differential equations. Mathematically, the material properties just, they enter the equations as what I call kind of scaling parameters. And they scale different terms in the differential equations. And that's going to cause the solutions or the results to have different behavior. Right? So that's how they affect our solution. I mean, in real life, we know how material properties behave, right? Material that's more dense is going to feel a lot heavier than it's not. But when you're talking about FEAs, it's important to know, exactly what effect or how it's going to affect your solution. Okay? At the end of the day, they just kind of end up just being scaling. Okay. But the idea of material properties kind of goes a lot deeper than just the values of certain constants. Okay. Because beyond the simple materials out there, there are a lot of different what are called material models. And this idea of a material model is probably something that has only been maybe very lightly touched upon in your previous classes, right? I think when typically when people first learn about solid mechanics, the focus is mostly on linear models or linear elasticity, linear isotropic elasticity. Okay, but in reality, there are a lot of different materials out there that don't follow that kind of straightforward linear relationship between stress and strain. Things like composite materials or biological materials, things like that. Okay. And so for those different materials, there are other models that we can use to model their behavior. And that becomes kind of incredibly important in FEA as well. Okay. So, we're going to focus our discussion mostly on linear elasticity, just because that's, probably hopefully what everyone's seen before. And it's what we're going to use the most in this class. But, there are other models that are out there. A lot of them are built into ANSYS actually as well, that we can use as well. The linear elasticity is just one model. It just kind of ends up being the simplest model. Any questions on this so far? Okay, so let's review linear elasticity. So, like I just mentioned, linear elasticity is the simplest material model that you can have. So linear elasticity gets its name by the fact that there is a linear relationship between the stress, the internal stress within the model, as well as the strain. Okay, so this is a plot that you've seen before. I believe we've shown this plot as well. So on the horizontal axis, we have strain, vertical axis, we have stress. Okay, and for a linearly elastic material, we have a linear relationship between the two. Okay, so there is just a straight line. So the more strain that you have, there is more stress that's involved as well. Okay, so what are the properties that go into a linearly elastic model? There's some familiar faces here. The first one we have is the slope of the line, which is the Young's modulus. So the Young's modulus E defines the slope of the stress strain curve in a linearly elastic material. And what the Young's modulus defines is how stiff your material is, how resistant it is to deformations. Higher value of the Young's modulus means that your material is going to be stiffer and harder to deform. All right, so certain materials that we associate to be tough, to be strong, materials like steel, they're going to have a higher Young's modulus, whereas softer material, maybe something like copper, are going to have a lower Young's modulus. Okay. Second property, we mentioned this before too, is the Poisson's ratio. Usually we give that symbol nu. So the Poisson's ratio normally doesn't play a direct impact into the stress strain curve that you have above. That's because Poisson's ratio is mostly for multi-dimensional structural mechanics, or multi-dimensional deformation. Okay. All right, so to put it in a nutshell, the Poisson's ratio basically measures how much the material will deform in directions perpendicular to the loading. Right, so if you remember kind of the discussion of this, I think it was maybe a couple weeks ago, right? So when you apply loading onto material, the natural thing it's going to do is it's going to deform, okay? But so if you apply a tensile force on a material, it's going to stretch out. You apply a compressive force on the material, it's going to kind of squish together, okay? So that's natural, but because whatever object that you're trying to deform has a fixed amount of mass, a fixed volume, you can't stretch in one direction and just not have it compensate in the other ones, okay? So the Poisson's ratio basically helps define the behavior of that kind of compensatory deformation that you don't normally kind of associate, or you don't maybe not normally see. Example, take a rectangle by tensile force. You're going to see is that the material will stretch out. But then to kind of compensate for that, to kind of compensate for the fact that the material is lengthening, you're going to see kind of a neck that's going to form as well. Okay? And the nature of that necking, or how much necking occurs, how narrow kind of that section is, it's defined by the Poisson's ratio. Okay. Now I know that's just kind of a qualitative description of it. Of course, there are equations that we can derive here that kind of define it, but I think for our purposes, just a qualitative understanding is good. All right. Any questions on this so far? Okay, good. All right, so those are the two main ones, and these are the material properties that we typically define when we are defining our own material in the in ANSYS. Okay. There's actually another one for a linear elastic material called the shear modulus. So the shear modulus specifically is a material property that basically tells you how well your material will resist shearing stresses or shearing strains. So this is a property, right? If you look up material properties of certain material, this is going to be there. The reason we don't really pay it too much attention is that for a linear isotropic material, we can actually compute the shear modulus based on the two properties that we just defined above. So the formula for shear modulus, the symbol for shear modulus is a capital G. Shear modulus is equal to E divided by 2 times 1 plus. So if you recall in activity 2, there was a point where we input the Young's modulus and the Poisson's ratio for our aluminum, right? Right after we did that, then ANSYS kind of automatically computed the shear modulus there for us. Okay, and the formula that ANSYS uses is this one here. So there's no need to input one manually, unless you have kind of a strange material that may be stronger in shearing or weaker in shearing. Okay, but for most materials, this relationship is pretty much satisfied if the material is linear and isotropic. Okay, so I've been throwing this term around today called isotropic, and so let's talk a bit more about what that means. We kind of mentioned it in the activity last week as well. Okay. Well, isotropic material, basically isotropic means that its behavior is going to be the same in any direction. Okay? It's the simplest, material along with linear elasticity. So linear isotropic material is the simplest it can get. Okay. Um, that's because there's no need for defining different behaviors in different directions. Okay. Okay. So what does this mean? So we have a cube of the material. And let's say that we load it in this direction. If you load it in that direction versus this direction, cubes aren't supposed to be different, they're all supposed to be the same, but statistically challenged, as my wife tells me. Okay. If you look at these three situations, the cubes are all identical. The only difference is that we're applying them loading in different directions. In all three of these cases, the total magnitude of the stress, the total magnitude of the deformation is going to be the same for an isotropic material. Basically, with an isotropic material, there is an assumption of symmetry in basically all three directions across the different types of stress and strain as well. Okay. Remember we talked a couple of weeks ago about there's normal stresses, shear stresses. So for an isotropic material, we're assuming basically a lot of symmetry. Okay. So, obviously, so far in this class, we've assumed all of our materials have been isotropic because, we've only just defined a Young's modulus and Poisson's ratio. So generally speaking, for a metal, most metals are going to be isotropic. Okay. So far, we've only just worked with metals, and so that's because that's the only one that. And the reason for that is, if you look at kind of the molecular structure of a metal, kind of what defines a metal is that all the molecules in the metal are very evenly kind of, organized and really, really well. So that leads to very even material properties. Okay. Any questions on this so far? Okay, good. All right. Another property of the linearity of a material is that, as you increase the loading on a material, on a linear material, you can generally expect the deformation to increase linearly as well. So what this statement here basically means is that if you have a simulation, and you're observing a certain amount of deformation or stress, if you increase the magnitude of the loading by a factor of 2, then generally, you can expect all the deformations and the stresses to increase by a factor of 2 as well. Okay. Okay, so for example, so actually a great example of this was the last activity that you guys did. So ANSYS activity 2. Okay. So for your bike crank, right? So the bike crank looks something like this. Yes. Right. We got 3 mounting holes here. Right, we're applying a force on one side. And originally that force was 100 pounds, okay? And so doing so would basically, produce a certain amount of deformation, a certain amount of stress in the part, okay? If we increase this force, and granted, this is the only load that's being applied on the model. If we increase the magnitude of this force by 50%, so let's say that we increase it to 150 pounds. What should you expect? So for a linearly elastic material that's isotropic, you should expect the deformations and the stresses to also increase by about 50%. And that's probably what you guys have noticed too in your activity. If you haven't, definitely go back and look at your results and kind of. That's essentially what it means to be a linearly elastic material. So, increasing the loading by 50% or decreasing the loading by 50%, you're going to see all of your structural results kind of increase or decrease by the same ratio. Okay. Now, this is an important point too. Just because this behavior or this trend also continues to kind of extreme values as well. So the lower end of the spectrum, we're not too worried about, and so, you can reduce the loading down to something that's very small. And that's usually not a problem, but the issue is usually actually when you increase by very large amounts. Okay? And so what's going to happen in the simulation is that if you increase the load by a large amount, then your deformation and stresses are also going to increase by large amounts. Which, you might be thinking like, duh, like that's exactly what you've been saying, right? And so if the whole idea with the linearly elastic material is that, you do get this kind of linear scaling increase, okay? But there is a limit to how much you can do this, okay? Because let me show you an example, right? So let's take our bike crank again. Take our bike crank. Let's see if we can draw it better this time. Kind of looks like okay. So let's say we go crazy, right? So we've run the simulation where the loading is 100 pounds. Let's increase the loading here to I don't know. Let's increase it to 9,001 pounds. So if our trend still kind of holds, then all of our deformations and all of our stresses are going to be multiplied by around 90. Okay? But and I'm just kind of throwing numbers out there. So let's say, for instance, in the 100-pound case, let's say that the deformation that we got was I don't know, maybe half a centimeter. Say max deformation. Okay. Right, and so if that's the deformation we got in the 100-pound case, it stands to reason, for a linear material, when we apply 9,001 pounds on it, then our deformations would be 90 times that. So under this case, deformation or max deformation so 90 times 0.5, that's 45 centimeters. Okay. But if the bike crank, if the overall length of this bike crank was, I don't know, let's say it's just 30 centimeters, okay, foot long. Having a deformation of 45 centimeters, doesn't really make a lot of sense, because that means that, this part right here is deforming down, to multiple length to actually over 50% of the length of this bike crank, which doesn't really make sense, right? So, you can't imagine you take a bike crank or a rod of metal and then deforming it in such an extreme way, and then for it to be okay after that. It's probably going to fail sometime. So this high value of deformation that we're getting is probably not realistic given the dimensions of the bike. Right, and so here kind of in lies the pitfall of using linear elasticities that, even though the linear assumption here is the simplest that you can do, sometimes it can lead to results that don't make sense, especially when you get to large magnitudes of load. Right? So generally the rule of thumb, when using linear elasticity is only really valid when your deformations are relatively small. And I'll put relatively small in quotes because it's one of those engineering terms that it's one of those things like if you know, you know, but if you don't, then it's like what is relatively small? So relatively small in my in my own definition is something that is less than 10% of the smallest dimension of your. And this, I'll preface this by saying this is my own definition of it. So other people have different definitions for what relatively small means. Um, so what this means basically is that you're going to look at your part, you're going to look at the smallest dimension. So the smallest dimension in this case would be the distance between the top and the bottom here. And so as long as your deformation is less than 10% of this, right? So not only do you take the small dimension, but you only take 10% of that, then I would say your assumption of linear elasticity is pretty safe, it's pretty good. Okay. Because this is one thing that ANSYS actually won't stop you by doing. So it won't stop you by doing a large deformation simulation. You can apply, a million pounds on this bike crank and ANSYS will be like, okay, no problem. So this is one thing you kind of have to look out for on your own. Make sure that you're really looking at your results to see if that makes sense. If it's especially egregious, then ANSYS may give you a warning, and so it may warn you that very large deformations have been observed, but it won't stop you. And so that's one thing you have to kind of be wary. And it's usually not something that you do like intentionally. And so usually for most people when they're running ANSYS, they're not going to intentionally put a million pounds. Usually it's something where like you're applying the boundary conditions and you're just typing things really quickly, and maybe you add an extra zero to the loading. And so just kind of make sure, just kind of be careful about this. So whenever you run a simulation, look at your results, see if it kind of makes sense. Because you'll be surprised. There's lots of really tiny errors that can kind of occur. I do them kind of all the time. Okay, so linear elasticity, really simple. Everyone loves it just because it's the easiest to understand, but it does have limitations, and you have to kind of. Any questions on this so far? Okay. All right. So before we move on to hyperelasticity, I did want to go through a couple extra points here with linear elasticity. Okay. So far, we've only gone over isotropic linear elasticity, which is material that has the same properties as molecules. Of course, not every material is like this. So depending on the direction of loading for certain materials, you may get different behavior. And this is quite common, right? And so I think probably the most common example that people refer to is wood material. So so the kind of the most distinguishing property of wood is that there are natural fibers that kind of run through the wood that were present there in kind of the tree that was that it had before it got felled and turned. So the direction of the fibers within the wood, will determine will change its material properties in those directions. But generally speaking, wood is stronger in the directions of fibers than it is in the directions of perpendicular to the fibers. And now, of course, that doesn't include, particle board or compressed wood that's made from sawdust. And so, this is kind of natural. All right, so another common material that has different strengths and different directions are certain kind of composite materials as well. Carbon fiber also very very popular kind of material in aerospace applications. That one also has different material properties. 3D printed materials, so additive manufacturing type of materials where especially ones where those are built kind of layer by layer. Those are also going to experience different properties and different. So nowadays, like I mentioned, kind of the trendy thing nowadays is to try to come up with new materials for different applications. So, and the more kind of complex materials that we have, the different kind of material models that we have. Okay. So we can modify our definition for linearly elastic materials to kind of suit these applications. So I want to make it clear that these next two material models that we're going to go through, they're still linear, right? And so there's still a linear relationship between stress and strain. It's just that we are accounting for essentially different slopes or different strengths in different directions. Okay, so the first one, probably the more simple one, is a linear orthotropic material. So a linear orthotropic material, basically, you're going to explicitly define the strength in each of the cardinal directions, as well as the different shear moduli in each of the different directions. You also have to define 3 different Poisson's ratios here as well. That's 3 normal moduli, 3 shear moduli, 3 Poisson's ratios. So in total, you need to define 9 different material properties for a linear. That's a lot. So that's not trivial, right? So if you compare that to our linear isotropic material, we only had to define 2. So we just had to define a Young's modulus, 1 Young's modulus, and 1's Poisson's ratio. So increasing from 2 to 9 is a lot. And usually, usually you're not going to be using this material unless you have some kind of like very detailed data sheet. So sometimes it can be hard to find, the data sheets for certain materials online for these materials, because running tests or running the experiments to get these material properties is quite expensive. So the companies that do perform these tests, they kind of keep them to themselves. But if you work for a company that's working on simulate a material that they're developing in-house, probably you're going to have the material properties and the data sheet to do this. Okay, because 9 parameters is a lot. That's not trivial. Okay. Okay. So that's linear orthotropic elasticity. The next step up is anisotropic elasticity. This is linear anisotropic. Okay. So this is the most general linear material model that you can define. Okay. So not only do you have control over the different directions in terms of the strengths, but you also have control over how the different stresses in each direction influence the other ones through kind of a more direct control over those, rather than kind of defining just a Poisson's ratio. And so, one kind of quick way to sum this up is that it assumes no symmetry at all. And so since it doesn't assume any symmetry, it actually increases the amount of parameters that you need as well. So these are exceptionally rare. And in fact, I can't even think of a practical situation where you would use an anisotropic material, just because it's so cumbersome. Because if an orthotropic material has 9, and anisotropic material is going to have a lot more than that. So the number of parameters that an anisotropic material has is 27. Right? So even the most detailed data sheets probably are not going to have 27 different material parameters. I can't even think of a material off the top of my head that would use this. And so this is kind of more like of a theoretical kind of material model that's used. It's used in the development for to develop isotropic material, but this is kind of the most general one. Okay. In fact, if you look at the theory behind this, there is actually a 4-dimensional tensor that's involved. So not, what a 2D tensor is. A 2D tensor is a matrix. A 3D tensor is just a matrix, but in 3D. A 4D one is, you can't even imagine it, because we only live in a 3-dimensional world. So yeah, it's crazy. It's definitely the part of grad school that I definitely slept through, but I slightly remember kind of the theory behind this. Okay. All right, any questions on this? Okay. All right, so let's talk very briefly about plasticity. I think we talked about it a bit last time, but let's review it again. Okay. So plastic deformation or plasticity refers to, kind of permanent deformation that can occur in a material if the loading or if the stress is high enough. So some people, view plastic deformation as kind of a departure from the linear stress strain curve. It's the stress or strain gets high enough. Okay, so that's one way to look at it. And plastic deformation is kind of the solution to, the issue that we talked about earlier. If you apply loads that are high enough, if you're assuming just a purely linear material, then everything's going to scale linearly. But once you kind of reach a certain point, the stress strain relationship in a material is not going to be linear. So I'm sure you guys have all seen the plots before. So let me go ahead and draw strain curve. So we've discussed this region so far. So that region is the linear region where stress and strain are linearly related. Okay. Slope of this curve is E. So if you're in that regime, right? So if you're in that kind of linear regime, kind of the assumption is that if you release the load, then your material or your model will relax to its kind of equilibrium state or relax to its kind of resting state. Right? So while you're in this regime here, then load is released. So that's I call that kind of the reversible regime. So you can load a material, you can load a part, release the load, and then it's just going to come back to where it was before. Okay. So that all that is Gucci, all that's good. But every material, every linear material, I should say, has a point where this relationship starts to kind of depart. Okay, so it's no longer linear. Right? And so the exact curve or exactly what it looks like, it kind of looks different for every material. But it starts to kind of look like the graph of the natural logarithm of x. That's how I think of it. Okay. So in this regime, we are entering what's called plastic deformation. So first of all, you'll notice that the curve is no longer linear, right? And so you start to have kind of a non-linear relationship between stress and strain. Right? But also, if you were to release the load, so let's say that you load a material enough so that it gets the plastic deformation, okay? If you release the load, the material doesn't actually go back to its original resting form. Okay? So let's say that you load a part all the way up until this point right here. Okay? If you release the load, this curve right here is releasing the load. If you release the load in the plastic regime, you're going to have some residual strain or residual deformation that's not there, even when you're not loading the part. Okay? So this point right here is the residual. And that's always going to be present as you know, if you kind of reach the plastic regime, you know, even if you release load, there's going to be basically permanent damage to your material, permanent damage to your part. Right? So usually, you know, for most cases, you know, if you ever reach plastic deformation, then you know that's basically considered like a material failure. Because another thing that we account for is the yield strength of the material. So that was in activity 2. So remember in activity 2, we said that the material will fail or the bike crank will fail if you reach the yield point. So the yield point is usually somewhere out here. So it's usually at a very extreme value of stress and strain. The yield point or the yield stress. If you recall from activity 2, you know, you know, we used the factor of safety. So we didn't carry the stress all the way to the yield point. You know, we had a factor of safety because usually, you know, well before you reach the yield point, because the yield point is absolute failure. That means the part completely just kind of breaks apart. Usually you're going to have effective failure before that. You're going to be well within the plastic. So when you're designing something, you're doing stress analysis, usually it's a good idea to add a factor of safety, okay? Just so that, you know, just so that you don't reach that. All right, any questions on this? Okay, so it's important to note that plastic deformation is not on by default in ANSYS. So ANSYS will, you know, by default will assume purely linear behavior. And that's mostly just for computational considerations. And so, you know, if you're assuming that the material is purely linear, it makes your simulation a lot cheaper, a lot faster to run. Okay. It is possible to do plastic deformation within ANSYS itself, but you have to turn it on. So there's a setting, and remind me to show you this on next Thursday because sometimes I forget. But there's a setting within ANSYS called large deformations. So it's within the analysis setting. So when you're opening ANSYS Mechanical, we haven't done anything with these settings, and so may not have noticed it up to this point. But underneath the boundary conditions, there's a tab for analysis settings. There's a check mark there for large deformations. We either turn them on or off. And so turning large deformations on will basically allow for non-linear deformations, essentially plastic deformations. But if you have it off, then ANSYS is going to assume pure linear. And so you can turn this on, and in fact, once I tell this to people, some people just turn it on all the time, and that's fine. Just kind of be aware your simulations will be a little bit more costly. Okay, any questions on this? Okay, the last thing I want to discuss today is this idea of hyperelasticity, which is a new, different kind of material model. It's not really, people have been discussing it for a long time. Okay. So, the way I think most people understand, or the way most people learn about elastic behavior, strength of materials, is based on the linear frame. So basically everything that we covered up to. But there are a lot of materials out there that have a very strange relationship, or a very kind of non-linear relationship between stress and strength. So there's a lot of materials that often don't have any linear regime at all. Especially in today's kind of modern age of people making their own materials. Additive manufacturing, 3D printing has kind of changed the landscape of this as well. Okay, and as we study kind of more biological materials as well, like tissues in your body, animal things like that. There's a need for kind of more robust and kind of more flexible material models that may not have a linear. Okay. And so, for instance, you may have a material model that might look like. So there's a lot of curves here, and there are maybe certain regimes that behave differently. So you can see there's a pretty flat regime where strain will kind of increase very rapidly, but then all the other parts don't have linear. Okay, so for these kinds of materials, there's been a new material models that have been developed, hyperelasticity. Okay. And the mathematics for hyperelasticity are actually quite different than what we understand as kind of linear elasticity. So the way a hyperelastic material model works is that it basically assumes that there exists a potential function called a strain energy function. And then through the strain energy function, then all the relationships between stress and strain are kind of derived off. Now, we can talk about hyperelasticity. This is something that we can talk about for, 2 or 3 or 4 lectures, just because this goes very deep, and that's why I encourage you to look into as well. But just in a nutshell, the way the strain energy function works, it basically assumes that every material has a certain amount of potential energy that's kind of naturally stored within the material. And so as the material is stressed, and so as the load is being applied to the material, it's going to choose a deformation state. So that's a certain configuration of the deformation that's going to minimize this strain energy function, or minimize the potential energy. It's basically a minimization problem. Okay. So the kind of the benefits of using a hyperelastic material model is that you can get very strange stress strain curves, and a lot of times these stress strain curves that result from this is a lot more consistent with the behavior of material itself. Okay. So kind of before the advent of hyperelastic material, people tried to use linear models to model like a viscoelastic tissue or composite material, and they would only be valid in certain regimes. And so it started to become kind of a mess where they would choose different linear models in different regimes, and it got out of hand very quickly. So hyperelasticity was kind of a response to this, where if you define the strain energy function, usually the strain energy function does not have that many parameters. And so you're thinking maybe probably 5, 6, maybe 8 parameters at the max. That's very attractive as well. So the number of parameters that you have to specify is small. Okay. And there are some hyperelastic models that have been kind of shown or verified to be very close to actual behavior for a lot of material over a much larger regime than just the linear models. Okay. So for example, one of the material models that I've worked with a lot in biological tissue is called the Mooney-Rivlin model. So in particular, the Mooney-Rivlin model is really good for modeling musculature, so muscle tissue. So muscle tissue is really interesting because it's material that often people describe as viscoelastic. And so it has kind of properties of a fluid, but also properties of a solid as well. And those have been kind of notoriously very difficult for, let's say, structural mechanics to really model their behavior, just because the fluid part kind of goes. But with a hyperelastic material, you know, it's very easy to kind of define that material behavior over the different. And this one in particular, the Mooney-Rivlin model, works particularly well for. So the thing with the hyperelastic models is that, you know, they're going to be named stuff that sounds really random because, you know, these are usually named after the people who discovered them, which is one of my biggest pet peeves in applied science, is because, you know, if I didn't tell you that the Mooney-Rivlin model was for muscle tissue, you know, you might read that and what is this, right? And in fact, if you look into ANSYS actually does have quite a few hyperelastic materials. You know, you're going to see a huge list of names that, you know, that doesn't make any sense unless you've actually worked in that field. So hyperelasticity, you know, goes pretty deep, you know, but you know, we're going to stay away from it mostly in this class. But you know, it's one of those things which is really. Any questions on this? Okay, all right. So that's all the time we have for today, and so we'll wrap it up for here. On Tuesday when we come back, we're going to start talking about meshes again. And we're going to be talking about different element types. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend. Stay dry, stay safe. I think the rain is going to continue for the next couple of days. So, you know, be careful out there. A friend of mine actually has gone to an accident today. So, you know, definitely, you know, want to be careful with that. Hope you guys have a good weekend. I will see you on Tuesday.
Yeah.
Jeff, go ahead. I don't know if I have audio here, so if you could type it. Yeah, flash break. Let me pull that up.
I kind of start over the color, so it's like. Well, my sister is getting.
Let me answer this question. Go.
She should have come back today or yes. I'm just gonna put that on and take it. Yeah. Oh.
Give it best.
والله جميل هو جميل يقرا الصراحه هو طويل شوي بس نعمل يعني هو طويل سهل سهل بس طويل هل تذكرت بعدين شو
My dad somebody else and he told me back after that it was his, so. I know.
Okay, you're wondering about the forces, right? Okay, so for the forces here, we have a pound of 150 pound, load of 150 pounds, near the bike, near the back wheels, and so I have 150 pounds here. Now, I think the exact surface that I chose for this, I think there's kind of a small lip that's kind of on the outside there. It's not exactly where the seat would be, but I just kind of picked that one just because it's the closest, for that. So even though it's on the side there, it's mostly okay. It's close enough. And then for the handlebars are attached up here. So this is where you would apply the 15 pound foot. I think so. Yeah, so point B here is where the 15 pound force is. I think I'm assuming that the Y direction is vertically. Yeah, the lip for both is perfectly fine. Yeah, so this model doesn't include the seat, it doesn't include the actual handlebar, so we're just applying the force on where they. Or close to where they. Already. Yep. Any other questions, Jeff, before I wrap it up? Okay, cool, have a good weekend.